In the last video, we looked at exploring the qualitative behavior of the mass spring damper system, as shown right here. And we looked at, we know we can solve this differential equation for various values of A, delta, omega, and capital Omega. And if they're given as specific numbers, you can use the complexification method to find the analytic solution. In the prior video, we explored the qualitative behavior that when the frequencies are close to each other, you get this beating phenomenon that we're seeing, and as they get way closer to each other, in this case exactly or near exactly equal to each other, right, you will get the resonance behavior. Okay, so the point of this video is to kind of explore a little bit more of the analytic reasons behind the qualitative behavior. So kind of exploring the relationship between analytic and qualitative. Okay, so what we're going to attempt to look at now is what we have covered, or what is typed up in the Google Drive under the mass spring forcing summary notes, and the notes are as shown here. Okay, so I'd like to point out some of the highlights. Okay, the idea that we've got waves in different forms and we're using the key complexification method formula. This is the key analytic tool. Okay, and for practice using that, you should look at the section 4.2 problems. Okay, if you use those tools on this differential equation, okay, but this differential equation where you've let the damping delta equal to 0, then the differential equation reduces to y double dot or x double dot plus omega squared x equal to, and for simplicity we're just going to let a be equal to 1. Okay, so now we have just omega and delta are the only things that can change in this problem. Okay, so we can see here that our homogeneous solution, because the eigenvalues come out to be purely complex, is going to be C1 cosine omega t plus C2 sine omega t for this differential equation. Okay, and if you go through the particular solution, find the particular solution, you can either use your guess as a cosine t plus a cosine capital omega t, b sine capital omega t, or you can complexify the force, right, to get alpha e to the alpha k e to the I phi e to the I omega t. You can use either way, but the solution you're going to end up with is that the particular solution, if you go through all the details, is going to be 1 over omega squared minus the forcing frequency squared cosine capital omega t. Okay. Notice that here's what's happening. Here's where we can see the resonance behavior. The relationship between the analytic and the qualitative shows up here. In the qualitative, when we were just looking at the graphs, we saw that something interesting happened when the two frequencies were equal to each other. If the two frequencies are equal to each other, then this term in the box, which is the amplitude of the particular solution, the amplitude is going to go to infinity because you get the division by 0. Okay, so once the two frequencies are equal, the amplitude of the particular solution goes to infinity. And that's why the resonance is happening. Okay? If the if capital omega and little omega are not equal to each other, okay, so these are not equal, but capital omega is close to the natural frequency little omega, okay, then you can take the homogeneous solution plus the particular solution, okay, and apply initial conditions, which are zeroed out. Right, so you set them equal to 0, and this will be your solution to the initial value problem, this particular combination of cosines. Okay? This particular combination of cosines, because of the trig identity, sine of A plus or minus B is sine times cosine plus or minus a sine times a cosine term. Okay, what we're seeing here is that the solution to the case when the frequencies are close to each other can be rewritten. Okay. So this term here, which is the solution to the differential equation where damping is equal to 0 and the two frequencies are close but not equal to each other, because of the trig identity, you get negative 2 over omega squared minus capital omega squared. Okay, and here's what I'd like to write here. Okay, there is a term, what I put here, these fast oscillations. You can think of this as amplitude A times the sine of capital omega minus little omega over 2 times t. That's what works out because of the trig identity. But what we're seeing here is that this amplitude changes with time. So this term right here is what I'm calling capital A. Right? And it's the amplitude of this trig function and the frequency of this trig function, okay, which I'll call the frequency slow oscillation, is little omega, big omega minus little omega over 2. Okay? So keep this in mind, that what we're going to see here is that in the case where there's beating, right, remember that there were these packets that were happening. There is this oscillation, and then it came down, and then it happened again, and then it happened again. So what you're seeing here is that there's some kind of trig function. That doesn't. I'll have to show you on the real picture. Kind of goes up, comes down, goes up, right? And it's happening in these packets. So if you look at the peak to peak time here, right, the period of what I'm calling the slow oscillations, the period of the slow oscillations is 2 pi divided by the slow frequency. So if you look at the difference of the two forcing frequencies and divide them by 2, and then divide that answer by 2 pi, that'll give you how far apart the peak to peak is on the packets. Okay, you can look at this term differently. Okay, this term right here, you can view it instead as some number b times sine capital omega plus little omega over 2 times t, right, where b is equal to this term, and b, the amplitude here, changes in time. Okay? And what that is controlling is that these are what I call the frequency fast term, the angular frequency fast. And that's going inside of these packets and looking at the peak to peak time of the little quick oscillations, which is 2 pi divided by omega fast. That is the period of the fast oscillations. Okay, so omega fast is capital omega plus little omega over 2. Okay, so just by using the sum of the trig identity, you can take your solution to your initial value problem and write it as a product of sine terms right here. And the product is much easier to analyze. Okay, so let's take a look at what I mean by this picture right here. Let's see if we can look at an example. Okay, let's add a page below, and let's look at the differential equation, for example. Y double dot plus 2 delta y dot plus omega squared y equal to a cosine capital omega t. Now we're only going to get beating. We're trying to analyze this beating phenomenon when damping is equal to 0. That's the only time it occurs. So we have the second derivative plus omega squared y equal a capital cosine of capital omega t. Okay. So let's let the natural frequency be equal to 2. And let's let the forcing frequency equal to 2.1. So those are pretty close to each other. And let's let amplitude A equal 1, for example. Okay. Now what should happen here is that we were going to get the differential equation y double dot plus 4y equal to 1 cosine of 2.1 times t. Okay. Now what we were going to see here was two different frequencies. Omega, it was the difference of the two divided by 2, and it was the sum of the two divided by 2. Okay, so that would be 2.1 minus 2 over 2, and that would be 2 plus 2.1 over 2, okay, which is 0.1 over 2, and it was 4.1 divided by 2. Okay, which you can convert these into numbers. Okay, let me see, which we were calling one of them the slow and one of them the fast. Okay, the fast was the omega term plus when there was plus. Okay, so we're going to call this right here omega fast, and this term would be omega slow. Okay, let's bring in our calculator real quick, and then I will look at the plot to see what these numbers mean. So let me bring in Mathematica, just my calculator. We bring in a new notebook, and then we will compute these numbers and see what happens. So 0.1 divided by 2, sure we can do this without a calculator, 0.1 divided by 2, and 4.1 divided by 2. Okay, so you'll get 0.005, and you'll get 2.05, which means that when you look at the period slow, that will be 2 pi divided by that number. Okay, and 2 pi, 2 times pi divided by a small number is going to be a big number, okay, which is 1256.64. And the period fast is going to be 2 pi over 2.05, which gives you 2.05, which gives you the number 3.065, for example. Okay. Now let's take a look about what this means. Okay, in this picture, we had decided that our differential equation had an A value of 1, so let's move A equal to 1, the forcing amplitude to be 1. We decided that we're going to let the natural frequency be 2, and the forcing frequency, we decided that was going to be 2.1. So notice that we get the beats phenomenon. I think maybe I made a miscalculation here. Let me double check something. 0.1 divided by 2 is 0.05. So this was supposed to be 0.05. 2 pi divided by 0.05. 2 times pi divided by 0.05 is 125, not 125.66. Okay. So let's see how the numbers we just computed make sense. Okay, I was calling one of these frequencies fast and slow, and I think that's what we're seeing in this picture. Right? We are seeing that, okay, look at the peak to peak time here. This peak to the next peak over there. It's at about 25, okay, right around here. The distance from here to here should be around 125, okay, which I think that would be consistent if I'm checking the timeline here. So maybe make time a little bit smaller. Oh, it's the distance between beats, I think. Let's see, it goes 1 period and then 2. So it's from here to here. Okay, so from there to there, it's made about, that's about 125 seconds to go from here to here. Okay, and if you zoom in on the time to make time quite a bit smaller, right, that, right, the peak to peak time in the, so we're going into this little packet here, and the time spacing from here to here, from peak to peak, is about the 3.065 seconds. Okay, so that's how the resonance case makes sense, and you can, so let me see, so the oscillations go up, max, they come down, right, and then they come back up again, right, so the peak was over here. So the distance from here to here is the 125 seconds, which we're seeing right here. Okay, so that's an analysis of the resonance case and the kind of the beating phenomenon case. Okay, and the rest will be homework.